We talk a lot about systems being resilient, but have you ever actually seen one save itself from a total catastrophe? Well, today we're going to do something pretty wild. We are going to pull the plug on a live, high availability SAP HANA database. We're going to watch in real time as its automated defenses kick in and rescue it from disaster. So let's see how it does. So here's our game plan. First, we'll dive into the architecture. See how this thing is actually built to survive. Then we'll do the pre-flight checks before we deliberately break it. After that, you'll get a front row seat for the automatic takeover, see how the system gets back in business, and then we'll wrap up by talking about why this kind of controlled chaos is so important. All right, first things first. Before we can really appreciate the magic of the recovery, we've got to understand the setup. Let's take a look at the key pieces that make this whole system so tough to take down. Now, the whole idea behind this is a concept called high availability. And look, this isn't just about having a backup tucked away somewhere. No, this is a whole design philosophy. It's about building a system that can take a massive hit, a critical failure, and just keep on running with barely a hiccup. For any business on SAP, this is everything. It's the difference between a tiny blip and a massive revenue-killing outage. Okay, so this diagram shows you all the key players on the field. Right there in the middle, you've got the primary node. That's our main workhorse. And right next to it is its identical twin, the secondary node. It's kept perfectly in sync down to the millisecond using something called HANA System Replication, or HSR. You can see the SAP applications are talking to the primary. And that eye at the top, that's the Pacemaker cluster. It's the brains of the operation watching over everything. You should really think of the Pacemaker cluster as the system's automated paramedic. It's not just sitting there. It is constantly checking the pulse of that primary node. And the very second it detects something's wrong, it is programmed to just spring into action and orchestrate the entire rescue, all by itself. Okay, time to prep for the test itself. Before you go and simulate a disaster, you have to be 100% certain that your safety nets are actually in place and ready to catch you. For us, that means going through 3 very clear phases. Our plan is really simple and methodical. First, we run through our pre-flight checks, make sure every light is green. Then, of course, the main event. We pull the trigger and manually cause the failure. And finally, the verification step, where we confirm that the system did exactly what we hoped it would, recover all on its own with 0 human help. And let me tell you, getting these green lights before we begin is absolutely non-negotiable. As you can see on our little checklist here, first we confirm that Pacemaker reports a totally clean bill of health. Check. Next, we confirm that HSR is in perfect sync. That means our secondary has an exact byte-for-byte copy of the data. Check. And finally, we make sure the SAP apps are connected and humming along. With that, all systems are a go. All right, this is it, the moment of truth. All our checks are done, everything's healthy, so it's time to introduce a little bit of chaos. We're going to simulate a complete and utter failure by taking out the very heart of our primary database. Our bullseye is a single process, and its name is hdbindexserver. Now, this isn't some background service we're tinkering with. No, this is the core engine of the entire HANA database. If this process dies, the database is gone. It's as simple as that. And this is the weapon we're going to use. The command kill -9. Yeah, that is not a gentle request. It's not asking the process to please shut down nicely. This is the system equivalent of a sledgehammer to the face. It gives the process 0 chance to clean up after itself. It is just terminated instantly and brutally, perfectly simulating a sudden, unrecoverable crash. Okay, we've pulled the plug. The heart of our primary database has just stopped beating. Now, we don't touch a thing. Our job is to just sit back and watch as the system fights to save itself. This sequence diagram just lays out the chain reaction perfectly. It all starts the moment the kill command is executed. Within just a few seconds, the Pacemaker cluster detects that failure. It immediately sends the signal to the secondary node, basically yelling, "You're up, go, 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 promote to primary." The secondary confirms it's ready, and the cluster instantly updates the network, telling all the SAP applications, "Hey, the new party is over here." So another way to look at this whole thing is as a series of state changes, like you see in this flowchart. The system immediately goes from a primary down state to a secondary active state. Then you see the data replication reverse direction, the virtual IP address gets moved over, and we land in our final happy state, apps reconnected. It's just a perfectly choreographed automated dance. And the speed of this whole process, it's just incredible when you lay it out on a timeline. At time 0, the process is killed. In as little as 5 seconds, the cluster knows something is wrong. By the 2-minute mark, the failover is already done. The secondary is the new primary. And somewhere between 3 and 5 minutes total, the applications are fully reconnected and back to work. Just amazing. So the database has successfully failed over. That's awesome, but it's only half the story. I mean, how do the SAP applications, which were just talking to the old server, figure out where to go now? The answer is, well, it's just pure elegance. This is where the magic happens, and it's all thanks to something called a virtual IP, or a VIP. See, the SAP applications aren't hard-coded to talk to a specific server's physical IP address. Instead, they talk to this VIP, which can float. During the failover, the Pacemaker cluster simply picks up this IP address from the dead node and assigns it to the newly promoted one. So the apps, they just see a brief timeout, they try to reconnect to the exact same IP they were just using, and boom, the new primary is right there waiting for them. Now for the final step, verification. We have to make absolutely sure everything worked just like it was supposed to. This post-failover checklist is our guide. We check the cluster status, confirm HSR is now syncing in the opposite direction, and make sure the apps are actually processing transactions again. We'll scan the logs for any weird errors, and most importantly, we run data consistency checks to prove that not a single byte of data was lost. So yeah, this was a really cool technical exercise. But it's so much more than that. Connecting this test back to the real-world business impact, that's what it's all about. Because the proof of a truly resilient system, it's always in the data. And here is that data. This is a sample test report, and it gives you the hard numbers. As you can see, every single one of our key metrics, the failover duration, the app downtime, the data lag, it all passed with fly-in colors. This is the objective, undeniable proof that the design works exactly as intended. Let's just focus on that first number for a second, 78 seconds. That is the total time it took from the moment the system detected a fatal crash to the moment a new server was fully promoted and ready to take over all operations. Just over 1 minute. That's it. And this number? This is the one that really matters to the business. 112 seconds. This is the actual amount of time that users and the applications were down. That's less than 2 minutes of downtime for what could have easily been a multi-hour, all-hands-on-deck, weekend-ruining emergency. So let's just put that all together. We went from a catastrophic sledgehammer-to-the-face crash of our core database to a full recovery with applications back online in under 3 minutes. And the most important word on this slide, by far, is automatically. No one got a panicked phone call. No one had to log in and frantically type commands. The system just healed itself. And that really brings us to our final thought for today. Watching this test proves what's possible with this kind of architecture. And it leaves us with a really important question to ask ourselves. If your most critical systems failed, right this second, would their recovery story be measured in minutes, or would it be measured in hours?